Things to remember when you're looking at probability distributions is that the sum of the probabilities has to equal 1. Each probability has to be between 0 and 1. Okay, so you can't have a probability greater than 1 or less than 0. Okay, so taking a look at these, if we look at the probabilities here and add them up, we get 1 point. So if we get the sum here, we get 1.4. So the probability, sum of the probabilities is greater than 1, therefore not a probability distribution. I need to change my... Okay, so that isn't. B, need to check it out. So here, when x is 0, what's the probability? So probability of x equals 0 is 1/2. Probability of x equals 1 is 1 over 1 plus 2, so 1/3. Probability of x equals 2 is 1/4. Probability of x equals 3 is 1/5. Okay, so you can probably tell that it's not going to equal to 1. But you can do it in your calculator or find a common denominator. So what's that? 30. So that would be 15 over 30 plus 10 over 30. Not 30. 4 doesn't go to 30. I guess 60. So 30 over 60 plus 20 over 60 plus 15 over 60 plus 12 over 60. So 50, 65, 77 over 60 is greater than 1, so not a probability distribution. Okay. In C, this has a negative probability. So the vertical axis is negative. Vertical axis is probability, and this is negative, so not a probability distribution. All right, so the next one, determine K for this probability distribution. So that means we know the probabilities have to add up to 1. And then from there, determine the probability of x equals 3. So probability of x equals 1 will be k times 1 plus 2. Probability of x equals 2 is k times 2 plus 2. Probability of x equals 3 is k times 3 plus 2. And so these all have to add to 1. Right? So that's going to be 3k plus 4k plus 5k equals 1. What's that? That's going to be 12k equals 1, so k is 1/12. So when k is 1/12, it will represent a probability distribution because the probabilities will add to 1. So that's our k value. And then determine the probability of x equals 3. So we put that back in here. So probability of x equaling 3 will be 1/12 times 5, which is 5/12. All right, so next page, looking at expectation or mean of a discrete random variable. So we're talking about probabilities here, right? So we already calculated the mean. We've been doing that for years, really, the mean of a set of data. Now we're looking at the mean of a probability distribution, okay? So that's the same as expected value. So E of x, it can be represented by the mean, mu. And for this probability distribution mean, it seems to always be mu rather than x with a bar over top. So these are interchangeable here, okay, for a probability distribution. We did this back in Math 20. I think we did the same question even. So calculating the mean or expectation of, in this case, this game of what you would win on one roll, okay, or one spinner. So this is a round spinner labeled 1, 2, 3, 4. And so we're assuming here it's a fair game, so that each part that's labeled 1, 2, 3, 4 is equally spaced, okay? That means the probability of landing on a 1 and a 2 and a 3 and a 4 are all the same. Okay, we would need to be told differently if this area here, say the area for 1 was a smaller spot, then that probability would be less, because the fraction of the total area would be less. Okay? If you land on a 1, you win $6. A 2, you win $3. A 3, you win $1. A 4, you win nothing. Okay, so those are the winnings. It says, assuming the likelihood of spinning 1, 2, 3, 4 are all equal, so it would look something like this. Determine the average winnings. Okay, this is also called the expectation. So that's where, if you take a look here, you're just multiplying the probability by the x value. So the probability for that x value by the value here. Okay, so what is the probability? You might want to just put it up top, okay, or below. You can write it out, but in this case, probability of spinning a 1 is 1/4, a 2 is 1/4, a 3 is 1/4, a 4 is 1/4. So they didn't give that to you, but they said it was an equal chance of getting any of those. So the expectation here will be probability times x, where x is the winnings here. So this will be 6 times 1/4 plus 3 times 1/4 plus 1 times 1/4 plus 0 times 1/4. Okay, that's the long way. Because the probabilities are all the same, it's really 1/4 times those winnings added together. So that's 10 over 4, which is what? 2.5. So in this case, it's money. So therefore, $2.50. Okay. So that's on average what you would win on a spin if you did this long enough. Obviously, you could play it a few times and always get 0 or always get 6. But this is the theoretical. If you play this to infinity, it would average out to be 2.5 average for every time you play. So, if the game costs $3 to play, is it a good game to play? No. So if they're charging you more than the average that you would get back, not so good for you, right? You might do okay, but if you keep playing it for a long time, you're not going to. And really, that's kind of what ends up like happening, say, like even in gambling in Las Vegas, right? There'll be a minimum bet on something. And they basically, the odds of winning will be, in the long run, will be lower than that average, right? Because in the long run, they always win, not the player. Okay, so $3 is greater than $2.50, therefore not a good game to play. So looking at linear transformations of expectation is the next part. Same kind of thing here. This game is developed such that a die is thrown where the variable x is the value on the side of the die. Okay, and the probability of rolling a 1 would be 1/6. A 2 is 1/6. So it's what do they call that? A fair die. Nothing's weird to it, right? They haven't weighted anything, so it lands all on one thing. Okay, so we're not going to fill this in quite yet. It says, part A, if the banker pays out the value of the roll in dollars, so that means this is actually going to be what you win, $1, $2, $3, $4, $5, etc. Calculate the expected value of that. So that's very much like the last one. Fastest way for doing this, because all the probabilities are the same, would be 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. So what's that? 3, 6, 10, 21 over 6. And that reduces to 7 over 2, which is $3.50 for winning. Okay. So again, if you were playing this game, you'd want to play it if it costs less than $3.50. You might want to play it, not necessarily. Okay, so now it says if the banker pays out $2 more, that should be $2 more, of the value roll in dollars, calculate E of Y. So you take a look here. So if this was the original, and now the banker's going to pay out $2 more than this, then this is going to be 3. This will be 4, 5, 6, 7, 8. Okay, now find the expected value of E of Y. So I've called that Y there. Again, the probabilities are all the same, but now we have 3 plus 4 plus 5 plus 6 plus 7 plus 8. $15, $20, $33 over 6, which is 11 over 2, which is $5.50. Notice how the banker was paying out $2 more for the roll on the die. Turns out when we compare these, the expected value is $2 more. So really, did you have to do it the long way? No. Okay, if you already knew the expected value of the original, and all you're doing is adding the same amount to each original X value, you can just add 2 to your original expected value. Okay. Then the next one, if the banker pays out 3 times the value of the roll in dollars, so now here, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9, 12, 15, 18. Calculate what you get there and compare it to what part A. So again, this we're calling Z. So 3 plus 6 plus 9 plus 12 plus 15 plus 18. Okay, so that's 30, 63. And 3 goes into that, 21 over 2. So that's the long way. You get $10.50. Compare that to the original. It's 3 times the original. So if you know the expected value of the original, we could just multiply it by 3. And that's really summarized in this linear transformations of expectation. This is a combined, right? So this is both doing a multiplication and an addition. We did it separately. But it's saying if you want to find the expected value by multiplying the original by something and adding, okay, that's the long way of doing it. That's what we did here. Okay, but it's also equal to the original expectation multiplied by that factor and then adding whatever you're adding on, right? So you don't have to go through and do the chart and this. You can just simply do that transformation. Okay. So then we get into variance and standard deviation. So here again, kind of like the variance and standard deviation of a set of data, now with a probability distribution. Remember the standard deviation, you're looking at the sum of the squares of the difference from each data value to the mean, okay? Now we're multiplying each by the probability. So that gives you your variance. And mu is that expected value of x. So most times when you calculate this, unless it gives you some of this information separately, you're really going to use this version here, okay? Because what is this? This is a little bit, tends to be a little bit easier. Certainly you don't want to go through every data value and subtract the mean from it. So most times you're not going to have to do that, okay? You'll end up doing this. So you'll either be given the expectation of x squared, or you'll have to figure that out, and then the regular expectation of x, all squared, okay? So this is the variable squared, then the expectation. This is the expectation squared, okay? And then obviously, just like before, standard deviation is the square root of the variance. So I think we did one similar to this in Math 20, but we're just going to do the variance from it, adding on, I guess, a question. So it says a store owner has determined the probability of a customer buying magazines in the store. The data is shown in the probability distribution table. So magazines bought per customer. Probability that happens is 0.1. One magazine is 0.23, etc. If you add these up, it says, is the data above a probability distribution? Well, let's add them up. And if it equals 1, which likely it's going to, because otherwise we can't answer the rest of the questions. So that's 0.33, 61, 83, 86, 96. It does work, right? 4, 12. Yeah. Just add that one. Okay, so sum of the probabilities. So really what you're doing there is 1. Okay, so the mean number of magazines a customer will buy, that's the same as the expected value. Mean in a probability distribution is the same as the expected value. Okay, so in this case, can't just show it in factor, we actually have to do it separately. So 0 times 0.1 obviously is 0, but you can show it in your notes just so you make sure that you understand.
times 0.13 plus 5 times 0.05.
Okay, whatever units this is, so this is number of magazine spots, so magazines. That's why they have them at the checkout at the store. They hope that you pick them up on the way. Although fewer and fewer people are doing that these days. Okay, determine the variance and standard deviation of the number of magazines a customer will buy from the store to the nearest 100. So, that's where we're going to use, oops, as I said, here, we're going to use, so EX squared minus E of X all squared. So the variance, E of X squared, okay, so thing here, we know this now. This is 2.19. We don't know what this is, right? So E of X squared, that's going to be, we have to take our probability and multiply it by the variable squared, each data value for the variable. So 0 squared times 0.1, which is obviously 0. 1 squared times 0.23. 2 squared times 0.28. 3 squared times 0.21. 4 squared times 0.13. 5 squared times 0.05. Should really have moved this over, so let's see here. So 1.77. Now, saying that both of these, that's the variance, and then the standard deviation, so variance is that, so lowercase sigma would be the square root. Keep the value that has more decimal places. Don't square root the 1.77. And then round. Nearest hundredth, which turns out to be 3 significant digits. Okay.